RoboDojo, a unified sim and real benchmark for comprehensive evaluation of generalist robot manipulation policies, July 2026.
Yeah, a completely brutal reality check for the entire field.
Right, so get this. The authors tested 30 state-of-the-art vision language action models. We're talking the biggest foundation models in robotics across 42 simulation tasks and 18 real-world tasks. And the absolute best generalist model, high-embodied 0.5 VLA, it achieved just an 8.8% average success rate in simulation.
Wow.
Yeah, and then in the real world, the top model, which was 0.5, it hit only 12.8%. Meanwhile, human teleoperators scored 76% in sim and a perfect 100% on the physical hardware.
So the hardware is clearly capable.
Exactly, but the models. We are nowhere near reliable general-purpose manipulation, and open semantic tasks, those are sitting at near a 0% success rate. So welcome to AI Paper Slap, where today we're diving deep into exactly why our leading models are failing so spectacularly and how RoboDojo actually measures those bottlenecks.
It's just, it is a really sobering data set if you're an ML engineer working in embodied AI right now, because, we've had this massive hype cycle around foundation models, right? Just scaling up parameters, throwing more teleoperation data at them.
Right, the bitter lesson.
Exactly. But what RoboDojo does is it effectively strips away that illusion of competence. It proves mathematically that when you force a policy outside of narrow, overfit, pick-and-place behaviors, the current state-of-the-art just completely fails.
Okay, let's unpack this benchmark structure, because you have to understand the proving ground and understand the failures. It's a dual environment setup.
Yeah, bridging sim and real.
Right. So on the simulation side, built on Isaac Sim, they have these 42 tasks. But they didn't just throw them in a pile. They mapped them across 5 specific capability dimensions, which are generalization, memory, precision, long horizon, and open tasks.
And then the real-world side has 18 tasks across 3 different robot embodiments, right? The ARX X5, the Piper, and the Piper X.
Exactly. And the whole thing is tied together by this infrastructure called XPolicyLab, which basically means you integrate your model once and you deploy it across both sim and real environments without having to write custom policy-side adaptations.
Which is huge for standardization.
It really is. Evaluating a model only in simulation is kind of like testing a self-driving car entirely on a perfectly paved video game track. Right?
Yeah.
It tells you absolutely nothing about how it handles a real-world icy road.
That's a great way to look at it, because past benchmarks usually just changed objects or, tweaked the lighting.
But called it a day.
Right, they called it distributional robustness. But RoboDojo forces policies to tackle distinct capability axes, like actual non-Markovian memory, or fine spatial precision, or contact-rich dynamics where the physics engine pushes back.
So let's look at the first domino to fall here, which is generalization. This is the simulation slaughterhouse. They tested these models on a standard layout and then a random layout where they just dump up to 25 clutter objects onto the table, mess with the lighting, change the background.
The messy desks scenario.
Exactly. And the performance collapse is just staggering. High-embodied 0.5 VLA goes from a score of 21.98 down to 1.57.
Thanks.
Yeah, a 92.9% drop in performance just from making the scene messy. Though models with 3D spatial grounding, like spatial forcing, they retained a bit more, dropping only 67.2%. But I have to ask, is this generalization failure just a vision problem? Like the model literally can't see the target object in the clutter? Or is it a low-level control problem?
So what's fascinating here is that it's actually not just high-level recognition. Even when the policy correctly segments and identifies the target object, the visual shift completely breaks their metric localization.
Wait, really? So it sees the object but still misses?
Yeah, the action grounding just starts to drift. The visual noise corrupts the precise coordinate mapping in the latent space. So the trajectory might miss by, say, 3 centimeters. And because these models can't recover from off-nominal states, that tiny miss cascades into a total failure.
Which perfectly explains the long horizon failures, too. Models like 0.5 show some progress there, but they fail at reliable skill composition.
Right, because the execution errors just accumulate.
Exactly. Step 1 drifts a bit, step 2 drifts more, and by step 3, it's just waving at the air.
Yeah, they lack the state verification to know if step 1 actually succeeded before moving on.
Here's where it gets really interesting, though. Let's talk about the hard stuff. Precision. XVLA leads this dimension, but it's still dismal. There's this insert key task where the policy will accidentally drop the key, but the arm just continues executing the insertion motion into thin air.
Without the key.
Yes. It's like a pianist who has perfectly memorized the sheet music, but their fingers are completely numb. They just keep playing the song perfectly, even if their hands slip off the keys, because they can't feel a thing.
That is exactly it. They lack closed-loop state verification. They're just blindly executing continuous join angles based on the initial visual input.
And what about memory? Models like EventVLA and XWEM show that having explicit temporal modeling helps, right?
It does help capture the historical state, sure, but the bottleneck is actually acting on that memory.
Oh, interesting.
Yeah, so the model might remember that the target is the blue cube hiding behind the box. But when it passes that information down to the control head, the physical grasp execution still fails. The memory doesn't buy you success if the low-level control is fragile.
Which leads us to the most brutal finding: the open tasks. These zero-shot open semantic tasks where skills learned in training have to be recombined dynamically for unseen language goals.
The success rates are basically zero.
Literally, the best model, 0.5, hit a 1.67% success rate.
Right, and it's because these strong vision language backbones are totally failing to align open-ended instructions with visual affordances and then translate that into executable physical actions.
The semantic action grounding is just broken.
Exactly. Large language models can output the text perfectly, but mapping that to 3D pixels and then to continuous joint angles in a physics-constrained world, it's incredibly difficult.
So simulation is a bloodbath. But let's talk about the physical reality check, the sim-to-real gap, because they ran the RoboDojo-RealEval across the 3 physical embodiments. 100% human success, proving it's physically possible. 12.8% for 0.5, which was the top real-world model. But the rankings didn't even align, right? Models like Galaxy VLA and Intern VLA A1 performed much better in real-world rankings than in sim.
Yeah, the sim leaderboard isn't a perfect predictor of physical deployment.
And then there's the safety aspect.
Yeah.
The paper mentions the DM0 model producing erratic oscillatory motions in the real world.
Yeah.
So aggressive they had to use the emergency stop.
Yeah, jitter.
So why doesn't a high simulation score guarantee real-world safety? What exactly is the real world exposing that Isaac Sim isn't?
Well, if we connect this to the bigger picture, real-world deployment introduces things Sim just glosses over. You've got perception noise from the actual cameras, actuation latency in the robot servos, and unmodeled contact instability.
So physics actually fighting back.
Exactly. In Isaac Sim, a jittery action sequence might just mean the object slips and you get a lower score. The rigid body dynamics are forgiving. But in the real world, a jittery action amplifies against the table surface. It creates this resonant frequency that destabilizes the entire arm. It breaks the robot or the environment.
Wow. Okay, so for the ML engineers listening, knowing how to test these models without breaking your hardware is critical. Let's talk about the engineering behind the evaluation, the throughput.
Yeah, the scale here is really impressive.
It is. For simulation efficiency, they used a heterogeneous parallel simulation on a cluster of 8 RTX 4090 GPUs.
10 parallel environments per GPU, right?
Exactly. Vastly improved throughput over older benchmarks. And the cross-GPU score variance was incredibly low, like a maximum of 1.1% deviation.
Which means the physics engine is finally stable enough to trust the parallelized leaderboard.
But the real-world efficiency is what blew my mind. RoboDojo-RealEval uses this web interface with a transparent image overlay of the reference layouts.
Oh, this was such a smart solution.
I love it. A simple, low-tech solution to a massively frustrating hardware problem. The human evaluator just looks at a ghost image on the monitor and slides the physical objects around until they match the overlay. They can reset a complex 5-object physical scene in an average of just 14 seconds.
It's brilliant. It guarantees reproducible initial states without needing expensive motion capture rigs or complicated robotic reset routines.
And then the scale of the data they provided to back this up, 1.86 million frames, which is over 20 hours, for sim training.
Yeah, and another 1.6 million frames for real world.
And that real-world data was collected via leader-follower teleoperation.
Right, which means it perfectly matches the kinematics of the physical robot. No mapping human hands to parallel jaw grippers. It's a massive gift to the community. Add in the double-blind scoring and shared remote cloud access for inference, and they've finally made physical robotics benchmarks as rigorous as NLP leaderboards.
So what does this all mean for you? If you're building the next generation of these systems, the takeaway is pretty stark. Scaling data and parameters just isn't enough anymore. Generalist robotics is totally blocked by contact-aware control and semantic-to-action grounding.
Yeah, I'll leave everyone with this thought. If Current VLA models completely fail at zero-shot open manipulation tasks, and they totally lack the closed-loop feedback to realize they've dropped an object. Do we need to fundamentally abandon pure behavior cloning architectures?
That's the big question.
Should the next generation of models be built on implicit physical world models rather than just mapping pixels to joint angles?
It's something the whole industry has to chew on. Huge thanks for joining us on this deep dive on AI paper slop. Check out the RoboDojo leaderboard as it continuously updates. We'll catch you next time.